In this video, I want to look at an overview of the Laplace transform, mostly as it applies to things in the real world. So in other words, what kind of functional forms do we get in the S domain after the transform has been taken? And then we'll do some examples or look at some examples of, given a certain form, how would you get back to the time domain, or at least have some intuition about what the time domain function would look like from the form of the function in the Laplace domain. So first of all, in the Laplace domain, we typically have functions that are polynomials in the numerator and the denominator. Typically, if we're modeling a real-world linear system, so something like a circuit, a mechanical system, sometimes even a chemical engineering control type system, if it can be represented by a linear differential equation, and it doesn't have things like unlimited inputs and outputs, typically it's a real-world linear system. And so even if the differential equation that represents it is inhomogeneous, the system itself is still a linear system. In that case, as a general rule, we'll tend to have a form of the function that describes the system in the Laplace domain that looks like some ratio of polynomials. So it's a rational function where n is a polynomial and d is a polynomial. N is the polynomial in the numerator. D of s is the polynomial in the denominator. Also, as a general rule for real-world systems that are bounded, in other words, they don't have limitless inputs or outputs, as a general rule for those kinds of systems, the numerator will be of lower order than the denominator. So that's typically what we find when we model an actual circuit. So before we do anything else, I want to pull up this list of Laplace transform pairs, and I want us to look at what different terms transform into. So terms that are in 1 over s represent step functions. 1 over s squared represent ramp functions. Terms that look like 1 over s plus a, where a is a constant, represent e to the minus at or exponential decay functions. Functions as shown here, where there is a constant in the numerator and then s squared plus a constant in the denominator, represent sinusoidal. Cosine is very similar, just having an s in the numerator. The 1 over s plus a squared term, which is similar to the 1 over s term, but it's squared, that represents what we would refer to as a damped ramp, or a ramp that's multiplying exponential decay. Furthermore, there's a damped sine and a damped cosine, and they have the following functional forms. So you can see that each kind of functional form in the S domain has a corresponding functional form in the time domain. So here is an example of a typical Laplace function and how it's simplified. So we start out with some n of s over d of s, and we place the polynomials n and d respectively in descending order of powers, each multiplied by the coefficient, and then typically you will factor out the coefficient on the highest order term in the numerator, as well as the coefficient on the highest order term on the denominator. So this one will come out as an a, this one will come out as a b. This will be a polynomial whose leading coefficient is 1, same in the denominator. an over bm is then given the notation k, which is a constant. And the numerator and denominator are then both factored. So with a polynomial, when you factor it, you have 3 possibilities. One is that you will get a real root, a unique real root. So s plus a. The other is that you'll get a repeated real root, so something like s plus a quantity squared. And then finally, you could get a quadratic that can only be factored into complex conjugate pairs. So those are your 3 possibilities, a real root, and I'm incorporating s equals 0 into that, so terms like 1 over s. or 1 over s squared. So a real root, a repeated root, or complex conjugate pairs. Each of those, as we just saw in the last slide, is going to correspond to a particular type of response in the time domain. So here's an example. This is a f of s here is a function in the Laplace domain, and so you can see that as we simplify that, we factor out the 8 from the numerator and we factor out the 2 from the denominator. That's going to simplify to 4, and then you can see in the numerator we have 2 roots. One root will occur at -5 and the other root will occur at -10. And then the denominator can be factored, and we illustrated previously in MATLAB how to find the roots of a polynomial. So the denominator can be factored, and it turns out that for this denominator it factors into 4 real roots, 1, 2, 3, and 4 all negative. So the other thing about a real system, first of all, it's going to be the denominator that actually predicts how the function, sort of the fundamental types of time domain functions. The numerator will represent some other things, like is that function, does it have a positive or a negative coefficient? What's its relative size compared to other terms, and so on. So let's go back one slide. I do want to point out that once you've factored this, the roots in the numerator are referred to as zeros, and the roots in the denominator are referred to as poles. And so, once again, a pole can be real, it can be complex conjugate pairs, or it can be a real root that's repeated. So from this example, we see that we have all real roots. So as we discussed before, as long as the numerator is of lower order than the denominator roots are what determine the time behavior of the system. And that could be exponential decay, it could be oscillation, it could be a decaying oscillator, or it could even be a ramp or a step. It is possible for poles and zeros to be complex. And so on the next couple slides, we'll look at some time domain functions for different expressions in the Laplace domain. We'll also show the poles on the complex plane. First though, here's just a summary. So we've looked on the table at what happens if we have distinct real roots. We have some constant over s plus a, and that inverse transforms into this e to the minus at. If this is squared, it's going to generate a t here. And by the way, if this was cubed, we would have a t squared. But we haven't really looked at complex conjugate pairs. So this is a case where you would have 2 of the roots of the denominator that form a complex conjugate pair. And they each have a corresponding numerator. And notice that the numerator k can be complex. And also notice that when I have k with the first root, I get k star, or the complex conjugate of k, with the second root. So in this case, the corresponding inverse transform is an exponentially damped, phase-shifted cosine function, where absolute value of k is the magnitude of the numerator, and theta is the phase of the numerator term. So one possibility is to write this root based on the fact that you have distinct complex roots. If you're using MATLAB to do a partial fraction expansion of your polynomial, MATLAB is going to output in this form. And so if it's output in this form, then this is what the inverse Fourier transform, or the inverse Laplace transform is. I think, hopefully I haven't said Fourier anymore in this lecture, but the inverse Laplace transform. All right, here is an example of what's referred to as the S-plane, or the complex plane. The vertical axis in the complex plane is the imaginary part of a pole and or zero. The horizontal axis is the real part. So if we look at -3 plus j4, the real component is -3, the imaginary component is j4, and the little circle means that this is a 0. And notice that anytime we have a complex root, whether it's a pole or a 0, its complex conjugate is going to be present, so we also have the -3 minus J4. We have a single real, the X represents pole, so we have a single real pole at -10. We have a pole at 0. We have a pole at -6 plus J8, and its conjugate at -6 minus J8 also shows up. Notice here that these roots are all on the left side on the complex plane, also known as the S-plane. And that as a general rule will mean that the system is stable. Most, if not all, of any circuits that you would model, especially in this class, you will always have your poles on the left-hand side of the real axis on the complex plane. Okay, the last thing to cover is the initial and final value theorem. So because functions in the Laplace domain actually represent physical systems in the time domain, we can sometimes work with the function in the Laplace domain directly instead of going back to the time domain, and a specifically useful theorem is the final value theorem. The initial value theorem is not used quite as often because the initial value theorem will not generate any initial conditions pre-existing before the transfer function was developed. So, for example, if you had some kind of initial voltage on a capacitor, initial value theorem, let me repeat. If you had initial voltage on the inductor, because that could change instantaneously across 0, the initial value theorem is not the best way to go about representing that. The final value theorem is often very interesting. So there are just two formulas, and that's it. The final value theorem, we basically take our function in the Laplace domain, we multiply it by s, and then we take the limit as s approaches 0. The initial value theorem, we do the opposite. We take the function in the s domain, we multiply by s, we take the limit as s goes to infinity. So this enables you to find initial and final values of quantities without inverse transforming back to the time domain. Okay, at this point, I'll pause the video, and in the next video, we'll look at some other things, including some examples.